In this module, we're going to be discussing electrical systems and ignition theory that is required to operate our small gasoline engines. So our objectives for this lesson are to identify and really review the components and parts of the ignition system in a small gas engine. We're going to describe how ignition occurs, and we're going to talk about common problems associated with ignition systems and how to troubleshoot those problems. So to review, the central component of the electrical system is the armature. In the Briggs Stratton engines, you'll see those labeled as magnetron, and magnetron is simply going to be their brand name for their components. But the armature is the more general name, is going to be the component that is going to create that electrical spark. With this, in all three of these examples, this part of the armature, and it's going to send the electrical current through the spark plug wire to the spark plug that's going to be attached here. We discussed this briefly the other day, but the early engines, and in the video we'll talk about this in a minute, utilize points and condensers. And the idea, or what happened, was pretty similar. There are some moving parts here, and at a certain point in the timing of the engine, a circuit will be closed, allowing the electrical spark to reach the spark plug. We'll talk about this in the troubleshooting a little bit, but moving parts in a small gas engine really just allowed for more things to go wrong. And so the development of the solid state armature over here with these models really cut down on issues that we used to see with the ignition systems of engines. We were just discussing some of the components of the ignition system in our small gas engines, and we're showing the pictures of the armatures as they evolve from the points and condenser system to this solid state armature. This is the particular armature that's on our Briggs 950 series, or our specific model, it's a 103G00. Either way, we'll have the same components of the spark plug wire, the spark plug attachment that actually we insert our spark plug, and then again this will be the end of the spark plug that's actually screwed into our engine, and this is in the combustion chamber where we have the gap for the electrical current to jump to actually ignite our air fuel mix. Set this to the side so I don't break that. And this curved area is what's going to ride right next to the flywheel, and this is the flywheel off of these engines. Other flywheels you may see in engines may have metal fins that's built into the face. This particular engine has a set of plastic fins that simply attaches when we put the flywheel cup on, which we'll look at those pieces in a minute. But again, to review, the fins simply keep air moving around the engines. These engines are air cooled, and it's going to get some air moving. This is the magnet that's going to really be the central piece of the flywheel that's going to create electricity. Remember, the other job of the flywheel that we've discussed is simply to be a big mass. And I don't know how many pounds this weighs, but it's pretty heavy for its size. And as it rotates, it's going to help keep the engine moving throughout the 4 cycles of the engine, or specifically the 3 cycles where we don't have power being created. The armature is going to ride, to move this into frame a little better here, very, very close to the flywheel. I'll say very, very close. We're talking about the thickness of an index card or a folded over piece of notebook paper that we can actually use to set our armature air gap. And if I do that, and I'll try to do it where I can remove this paper, and you can see that from your angle it actually looks like it's touching, but it would actually be able to spin. We don't want it touching because when we get too close to the magnet, it's rather strong, and now we couldn't rotate it with our recoil starter. So as this flywheel spins, it's going to spin by these. There's several layers of thin metal that are connected into this solid state composite armature. That there's a coil of wire in here that's actually going to create a high voltage electrical current to be sent to the spark plug at the correct time. And we'll get into the exact meaning of timing in another video, but the central point of timing in the electrical system is actually going to be the flywheel key, which is going to ride right here, so that we are attaching this flywheel to the crankshaft in 100% the correct place for this to happen. And so what happens is we have this flywheel, we have that, again, that plastic set of fins, and we have this cup that's going to have to be in the exact right spot here, and it's going to ride and be bolted here to the end of the crankshaft. And this is going to allow us to have our recoil starter, so that when we pull our rope, this is starting to spin. You'll see that on the side of your frame, that silver piece of metal right here come out. This is going to catch in this flywheel cup and start the engine spinning. And the force of your arm spinning this flywheel is going to create the electrical current to get the engine started in the first place. So again, some of the main components that we're talking about with the electrical and ignition system is going to be, I'll start kind of small, the flywheel key, which is going to be a small piece of metal that's going to ride here in this notch in the flywheel, and also a corresponding notch in the crankshaft itself. The flywheel magnet, the flywheel cup, and I'll take it out to the actual recoil starter that we have to pull. We'll have our armature, and finally our spark plug. That's going to complete pretty much most of the ignition system. Well, again, we'll have a kill switch and a kill wire that's also part of the ignition system, but those are an added feature really to be able to turn the engine off by eliminating or grounding out the flow of electricity to the spark plug. So a very important system, relatively few parts, but we'll see a video in a few minutes that does a really good job of kind of explains what's going on in this this part. And I think you'll see that when we get into anything in the world of electricity creation, and electrical theory, relatively few simple parts can get relatively complicated fairly quickly. And that video will do a great job of explaining this. So as we reviewed the components of the ignition system, we'll keep in mind that, once again, the entire function of this ignition system is to create electricity that is used to ignite the air-fuel mix within the combustion chamber of the engine, and the spark plug is the actual piece that's going to do that. Most small engines, and in fact pretty much all modern small engines, are going to use that solid state or that one-piece magneto to produce electricity. With that, remember, that magnet spins by the armature. Older Briggs Stratton specific engines, like pre-1980s, you might run into one at some point that has that point-in condenser. They can be fixed and they can be used, but Briggs makes a very handy retrofit kit to modernize the ignition system. And once you do that, you pretty much minimize the risk of failure in the electrical system once you get rid of the points and condensers. So the next slide is going to be about an 11-minute video for Briggs Stratton that's going to start with a brief history of how ignition systems came to be in small gas engines, and it's going to run through a little bit of electrical theory. Some of this should sound pretty familiar from when we did our unit on campus at LSU with what we talked about when we're talking about residential electricity. The biggest difference is we're going to be mostly in the world of DC, or direct current, in our small gas engines, but the same terminology, the voltage, amperage, should sound familiar, and you should hopefully remember what those terms mean.
The Otto Langen atmosphere engine, introduced in 1867 at the World's Fair in Paris, France, offered 2 horsepower for all of its 4,000 pounds. This engine was not a 2-stroke or 4-stroke, nor did it even have a crankshaft. Power was captured from a free-floating piston that was propelled by an explosion of fuel and air. The ignition system was ignited by an external flame from a Bunsen burner. Within 10 years, Otto would design, build, and patent the first practical four-stroke internal combustion engine, called the Otto cycle engine. Early ignition systems were a challenge. Batteries and electrical components in general were in their infancy, and early examples designed for ignition systems were poor at best. Open flame and hot tube systems were often used on stationary low-speed engines. Some farm engines were even started with a kitchen match. The open flame system introduced an external flame, usually from a burning gaseous fuel, into the combustion chamber. The hot tube is almost like a glow plug for a diesel system. An external flame heats a tube to red hot. One end of the tube is in the combustion chamber and ignites the fuel-air mix. Early on, the magneto became popular as a self-contained ignition system. No battery is required. This simple design rotated a coil of wire within a magnetic field, which induced a flow of electricity in the coil. At a pre-established point, the igniter, or point set, would open and spark would occur, igniting the fuel-air mix. The armatures pictured on this page are examples of modern Briggs Stratton ignition systems. The unit on the left is from a contact point system, which saw service for about 30 years, up until the early 1980s. The center armature is a composite magnetron, which is a transistor-controlled system. Composite refers to the epoxy that encompasses the armature body. Magnetron is a registered trademark coined by Briggs Stratton for this type of system. The standard magnetron armature replaced the contact point ignition system and was the lone ignition system until the composite advancing style magnetron was introduced in the late 1980s. Both standard and advancing have been available ever since. Briggs & Stratton engines have employed magneto ignition systems almost exclusively for 100 years. Magneto is short for magneto-electric machine and has been defined as an alternator with permanent magnets used to generate current for the ignition in an internal combustion engine. At the heart of this simple system is electromagnetic induction. Where an electromagnet is the generation of a magnetic field by passing electricity through a wire wrapped around an iron core, the function of a magneto can be described as the generation of electricity by moving a wire wrapped around an iron core through a magnetic field. As was already discussed in the section on electrical theory, when magnetic fields and conductors are brought together, the potential exists for electrical energy. In order for this to occur, the magnetic field must be either a changing magnetic field or a moving field. Changing can simply be expanding or collapsing. Moving is physically moving the magnet as in the rotating flywheels used on most small engines. An alternative is moving the conductor through a stationary magnetic field, which has the same results. In some cases, the magnets are stationary and the conductor moves. This approach is often used in DC electric motors. The switch or contact point is closed, creating a complete circuit through the winding. Movement causes the conductor to cut through the magnetic lines of flux emanating from the magnet. This causes electrons to flow through the winding. Electrons moving through a winding of wire wrapped around an iron core describe an electromagnet. This is virtually the same as an electromagnet created by attaching a winding of wire to a dry cell battery, but without the battery. In this case, the flow of electrons is induced by the magnetic field and describes the basic principles of electromagnetic induction. Note here that the winding of wire is now enveloped by its own lines of magnetic flux. Let's add some parts. Pictured here is the entire schematic for a contact point type ignition system, also known simply as an inductive ignition system. The blue lines are another winding of wire wrapped over the red coil. The red winding is called the primary winding, and the blue the secondary winding. Note the potential circuit for the secondary winding. One end of the wire is grounded, while the other terminates at the center electrode of the spark plug. Electrical energy cannot complete a circuit through the secondary unless it can be persuaded to jump across the air gap of the spark plug. The combination of the two windings effectively fits the electrical definition of a transformer. The primary winding is 74 turns of wire, while the secondary winding is comprised of approximately 4,400 turns of a fine copper wire. For every turn on the primary, the secondary has 60, for a ratio of 60 to 1. This ratio establishes that our transformer is a step-up transformer. A step-up transformer increases voltage in this case by a factor of 60. A condenser is added to the primary leg of the circuit. When the contact point set closes and the flywheel magnets move across the iron core, energy immediately begins to flow through the winding. When they open, energy flow is interrupted. Both events can cause arcing across the contacts, which can reduce their useful life. The condenser absorbs some of the energy to reduce arcing because a condenser is a storage device for electrical energy. It offers the added benefit of dumping energy back into the circuit to enhance the system's output. Now let's see the system in action. As the flywheel magnets move past the lamination stack of the ignition armature, the points close. The moving magnetic field causes voltage to build and current to flow through the primary winding. The faster the magnets move, the more energy is developed. The primary circuit of the ignition armature is capable of developing approximately 250 volts at 2 to 3 amps. Because of their proximity to each other, electrical energy flowing through the primary winding creates a magnetic field that engulfs both windings. Some mechanical event, often caused by the cam gear or crankshaft, will cause the points to open. The magnetic field encompassing the primary and secondary windings collapses. A collapsing magnetic field is a changing or moving magnetic field. It is virtually the same process as moving the flywheel magnets past the ignition armature. The main variable is the speed at which the field moves. The flywheel is limited to the top no-load speed of the engine. A collapsing magnetic field travels at near the speed of light. This high-speed event, coupled with the 60 to 1 ratio between windings, creates a huge surge of energy in the secondary winding. To determine the approximate potential, multiply the voltage potential created in the primary by 60. The primary is capable of approximately 250 volts times 60, which equals 15,000 volts. Although this ignition armature is capable of 15 kilovolt, it will seldom be called upon to provide this much energy. The armature will only generate the energy required to jump the gap of the spark plug. Understand that several variables come into play here. A warm engine will run on about 4,000 volts of energy. To run a healthy cold engine may take 8,000 volts, with a little bit more thrown in to start it. To overcome the resistance value of air may take 2,000 to 3,000 volts. The resistance changes, however, when the spark plug electrode is under compression, causing the energy requirement to virtually double. The customer who pronounces an ignition system as good after laying a spark plug alongside a cooling fin and pulling the engine over has not sufficiently tested the system to make that claim. Contact point ignition systems begin to deteriorate as soon as they are installed. Even though Briggs Stratton point set contacts were chrome-plated for better wear, and the technician burnishes the surfaces on installation, oxidation begins when exposed to air. This is most likely to occur during prolonged periods of inactivity, and is often at least partly responsible for the common customer comment, "It worked fine when I put it away." In the 1970s, the message from customers became clear that a better system was needed. Although a variety of electronic ignition systems existed at the time, most were too bulky or expensive to use on a walk-behind mower. Briggs Stratton engineers designed a transistor-controlled ignition, or TCI, to replace the contact point set. This system added two simple components to the point ignition armature: a transistor module comprised of a Darlington transistor and a trigger coil, which controlled when the coil should fire. The primary and secondary windings of the armature continued to supply the energy required to jump the spark plug gap.
So when we start thinking about potential faults and failures in the ignition system of small gas engines, you need to determine the type of ignition system that you have. Again, if it's an older, in Briggs' world, it's pre-80s, other brands probably pretty similar. I'm not particularly sure on some other brands, but if it's pre-80s, Briggs & Stratton has that points and condenser system. That was historically the most common problem for ignition-related problems, with some sort of issue with it. It could be the timing or the opening and closing of the gap, moisture preventing the electrical spark from occurring. Briggs pretty much recommends that retrofit kit to introduce a solid-state armature to those older engines, and once that's accomplished, there's very little to go wrong with these modern ignition systems. Nevertheless, problems can and really do occur because we have moving parts, we have mechanical systems, and we still have human error. So often we identify that we have an issue with our engine. It won't start, and it's sometimes tempting, if you're one to want to fix problems yourself, to start taking things apart. But I've noticed in teaching small engines for a few years that this it's usually not the right pathway to go. It's best to first think through the problem. I think about the symptoms the engine is exhibiting, and try to determine and think through what's possibly going on. And always remember, we didn't talk about four-cycle theory and the four strokes of the engine for no reason. Something is happening. Remember, we talked about the 5 things that needed to happen for engine operation. One of them is ignition. So let's say that's where we've determined through some symptoms, and we'll talk about symptom information when we get to a deeper troubleshooting unit here in a couple of days. But before you jump in, you start removing big components to try to get after the armature or the flywheel. Check the easy things first. Always starting with the spark plug if we're in the world of electrical system. Is it fouled? What does that mean? It means that that spark plug, the end in the combustion chamber is dirty. It's full of carbon. It could be oil, and then that could lead to another issue. It could be misgapped somehow. Maybe it was put a new spark plug in, you didn't realize that you set it down too hard, or maybe you dropped it and it closed the gap, or perhaps it was just made wrong and it's not gapped correctly, it's too wide. Older spark plug, we used to have to gap them all. They pretty much come pre-gapped now, but it's never a bad idea to use our feeler gauge or our spark plug gauge to check that gap. Visually assess the lead wire, the spark plug wire. Maybe it got cut. Maybe it's got a gash in it and it's allowing it some contact to metal somewhere and it's grounding itself out. Did you store that engine over the winter, and did a rodent or a raccoon or something get in there and chew on that wire? Lots of times our problems are pretty simple. Perhaps the kill switch is engaged. It's going to have a circle and a line on it, and you're probably going to forget which way is which. So make sure you pull that starter rope with it in both ways, and see if it's simply that you have the kill switch engaged. And before you remove the flywheel, check the flywheel key that we talked about in the parts lesson earlier. Maybe if it's a push lawnmower or walk behind lawnmower, did you remember, did you hit a rock, did you hit a stump? Because that flywheel key, in addition to making sure the engine is timed, it's also made to shear or to brake, to protect more expensive and more crucial parts of the engine. If it's just spinning freely when you pull the starter rope, you're not going to engage the flywheel, and it's not going to spin by the armature and create electricity. So before we start removing the big components like the armature and the flywheel, check the spark plug, the lead wire, the kill switch, and the flywheel key before you just really start taking some of those big components off. Another check that I forgot to mention on the previous slide, in addition to the spark plug, the spark plug wire that we talked about before and the kill switch, is actually an oil sensor. If you look on the outside the crankcase in most small engines, you see a little module on these 950 series or these 103G model engines. It looks like a little silver, not quite a cube, but a half of a cube, so a square. And on the inside of the engine, there's actually a receiver module. And if there's not enough engine oil in the crankcase, it will prevent the armature from being able to create electricity as the spark or as the magnet passes the armature. And this is a safety feature that Briggs and probably many small engine companies, manufacturers, have actually added to ensure that the consumer checks the oil regularly, or even probably more importantly, when the engine is brand new, engine oil is added because all the engines are shipped with the crankcase free of oil. So again, one more check in the ignition system is actually an oil sensor that's within the crankcase that's going to prevent electricity from being created if there's not enough engine oil in the crankcase. After this slide, I've got a short Briggs Stratton video about electrical troubleshooting that might bring some more of these pieces together that we've talked about.
Testing Briggs & Stratton magnetron systems is quick and simple. The recommended tool is the 19368 spark tester. When attached to the high-tension lead, the tester introduces an air gap to the circuit, much like that of the spark plug electrode. The air gap offers resistance. The greater the resistance, the higher the voltage must be to push energy across the gap. The technician simply removes the spark plug boot from the plug, reattaches it to the connection on the tester, and secures the alligator clip to a good engine ground. The rewind rope is pulled, simulating a starting attempt, while the window in the tester is monitored for spark. If a steady succession of arcs jumps across the window, the ignition system is assumed to be healthy. Electrical components are occasionally known to fail only when hot. This situation can be tested as well. To set up for this test, the tester is installed in series between the high-tension lead and the spark plug terminal instead of an engine ground. The engine is started and allowed to run. The technician then waits for the engine to heat up and begin to fail. Once it begins to act up, the spark tester window is monitored for steady spark. If the arc goes away or becomes intermittent, the ignition system requires further investigation. If the arc remains steady in the window, the technician knows the ignition system is most likely not at fault. Let's take a look at typical ignition system problems. We'll start with a sheared flywheel key. This is perhaps one of the most common ignition system problems experienced, particularly if the engine powers a rotary lawnmower. The mass and speed of the rotating blade and the engine flywheel grant them a fair amount of kinetic energy, which is released abruptly if the blade strikes a rock or a stake in the lawn. If the energy is sufficient, the blade and/or crankshaft will bend and the flywheel key will shear. This is far less likely to occur on engines that connect to equipment by way of belts or other devices that will absorb some of the shock of a quick stop. Next is a worn, fouled, or defective spark plug. As a plug wears, the voltage requirements to jump the air gap become greater and greater. At some point, the system will begin to break down. Fouling generally offers an alternative path to ground that bypasses the gap so no spark occurs. Defective plugs generally have additional resistance within the plug body due to damage or connection problems, which hamper or prevent output. Cranking speed that is not fast enough can also be a problem. To activate the armature electronics and build enough energy in the secondary to jump the spark plug air gap, the flywheel must spin at a minimum speed of 250 RPM. A shorted remote stop terminal wire can also be an issue. Most engines now use some sort of wiring harness that ties the ignition armature stop terminal to a remote magneto stop terminal, possible equipment safety switches and/or blade stop devices. Because of the significant vibration characteristics of powered equipment, wires have been known to short out. When troubleshooting a failed or intermittent system, it is more likely to find these circuits at fault than a defective ignition armature. And last but not least, a poor ground between the armature and the cylinder block can be an elusive problem. Another circuit that can cause trouble is the ground circuit between the armature lamination stack and the spark plug. The leg of the circuit in question is that from the threads of the spark plug to the lamination stack of the armature. If a problem is to develop, it is most often the connection affected by the attachment of the armature body to the cylinder block. If corrosion develops here, the circuit is compromised and the ignition pulse may fail altogether or become intermittent. There are also problems that have been known to happen but are categorized as unusual. An incorrect armature air gap is included in this area. Testing shows that for many, if not most Briggs Stratton engines, the armature air gap cannot be made too wide that it will prevent the engine from starting and running. The high-tension lead is attached to the secondary winding by impaling the core of the wire with a post attached to the winding. On rare occasions, oxidation at the contact point can increase resistance and weaken or stop the armature from functioning. This can be identified with a meter set to the ohm scale. Connect one lead of the meter to the spark plug terminal end and the other lead to the lamination stack. The reading should be between 2,000 and 5,000 ohms. The high-tension lead is not replaceable. Ignition armatures can be defective, but this is fairly unusual. To troubleshoot, test for spark with the 19368 spark tester by pulling the engine over at a minimum speed of 250 RPM. If there is no spark, remove the blower housing and isolate the armature by disconnecting all wires at the armature terminal. Test again. If no spark, remove the armature and clean the contact area with the cylinder block with sandpaper. Remount the armature and check. If no spark, replace the armature. Aftermarket spark plug boots made from substandard material have been known to oxidize over time. The oxidized material is often conductive and has been known to shunt the ignition pulse to ground by shorting the path to the blower housing. Modern-day magnets seldom lose their charge, but there are situations that will cause them to fail. Magnets do not abide extreme heat or cold and mechanical shock. Striking a magnet with a hammer can cause some loss of the magnetic field. To test the strength of the flywheel magnets, hold a 10-inch No. 2 flat blade screwdriver to the magnet. The magnet should be strong enough to hold the screwdriver straight out. The correct spark plug for a particular engine is selected by part number from the illustrated parts list. As a spark plug wears, the center electrode is rounded off. This is due to the constant blasting away of material by the arc. As the sharp edge is reduced, the ignition system voltage requirement rises higher and higher because electrons are more easily emitted from a sharp point. At the same time, the gap gets wider, also requiring more voltage. Eventually, voltage requirements exceed the ability of the armature to keep up, and the ignition system fails. Here are several statements based on rules of thumb that have been around for years. Do you agree or disagree? Number 1. Rust on the flywheel magnets causes a loss of spark. True or false? False. Rust is not a barrier to a magnetic field. Number 2. When checking magnetron ignition armatures for spark, a bright blue spark color is best, and a yellow-orange color is weak. True or false? False again. Spark color is primarily a result of what compounds are in the air between the contacts of the spark tester when the arc occurs. Just as fireworks are colored red, blue, or green by different chemicals, salts that are common in the air result in different hues. Orange and yellow come from particles of sodium in the air, ionizing in the high energy of the spark gap. Number 3. Laying the spark plug on the block and pulling the engine over can adequately check the ignition armature output. True or false? False once more. Even though a spark jumps across the gap of the plug when grounded to the engine block, this is not a measure of the energy reserves the system has available. The voltage requirements will double when the plug is under compression in the combustion chamber, because the air density has changed. Number 4. The ignition armature can be adequately tested by using the 19368 tester and pulling the engine over a minimum of 100 RPM. True or false? False. The system has to develop a minimum voltage to activate the electronics in the armature, and it has to be capable of a minimum voltage output from the secondary winding to be able to jump the air gap of the spark plug. The minimum cranking speed for magnetron ignition armatures is 250 RPM.